Good afternoon, everybody. I'm here with what I at least consider to be an interesting problem. And I'll just read it to you. You can read it, but just to get our feet wet here. A mathematically inclined West Texas high school principal wants to optimally utilize her new commodious, spare no expense gymnasium paid for in large part by oilfield money. Now, so she's toying with these three different seating configurations. Now, she knows how many people are scheduled to graduate, okay? And so the question here, and there's more than one question you could ask, it says how many students are scheduled to graduate given the possibility of all three of these seating configurations. Now, one of the configurations is each of the rows can seat 13 people, but that would leave 8 in the last row. Condition 2, the other condition that's possible, is each of the rows are of size 15 with 3 left in the last row. And finally, the rows have size 19 with 15 left in the last row. Now, of course, here, what's not known is the number of graduates or the number of rows. So to me, it's kind of fascinating that even though those things aren't given, the fact that we're being given these remainders, basically 8, 3, and 15, okay, and the size of the rows, that's enough information to uniquely determine how many people are going to graduate from this high school. All right, now let's get busy here. A little bit of notation. We'll go ahead. The standard variable unknown in math is x. So x is going to be the number of graduates we're seeking. Now this r sub I is just the number of rows per condition. So again, we don't know the rows, but if you look at condition 1 here, condition 1, and come over here, this describes it in terse mathematics. You see, you have an unknown number of rows, 13 people per row, okay, with 8 left in the last row. Now, notice what I've done here is I've just exhaustively written out some possibilities, 21, 34, and you can do the calculations there. But if there were 2 rows, that would be 26 plus 8, which is 34. All right, and so on. You can see what's going on here. This is hopping along at multiples of 13. Now this condition number 2, where you can have 15 per row, it starts out at 18 if there's just 1 row, and then you increment along at 15. And finally down here, this is the third condition. You can see what's going on here, 34, and then you increment at 19. Now notice the only overlap so far in this exhaustive approach is we have 34 here and 34 here. Now you could, if you were so inclined and had enough time, you could do this exhaustively. You could just fill out all these forever and ever and ever. Probably get repetitive stress syndrome in your hand, but you could eventually stumble upon the answer in a not too sophisticated sort of brute force approach here. All right. So again, you could go on and on and on until both of these sets contain the same number, and that would be your solution. Now, I'm proposing a more sophisticated way of looking at this. This is these 3, what they call congruential equations right here, describe the circumstances here. Like this very first one that says x is congruent to 8 mod 13. This is called modular arithmetic. That's equivalent to saying that x minus 8 is a multiple of 13. This is equivalent to saying x minus 3 is a multiple of 15. And this is equivalent to saying x minus 15 is a multiple of 19. And if you look at these statements over here to the right that we've written down, that if you brought 8 to the other side, that would say x minus 8 is a multiple of 13, the multiple being the number of rows. This would be x minus 3 is a multiple of 15, R2 being the number of rows, and in a similar fashion right here. And again, as I mentioned earlier, there's a way to do this. You can do it if that's what you feel, how you want to spend your time with COVID. In the pandemic, we all have a lot of time on our hands, I suppose, and you could go through this, but it's not too uplifting or edifying to do it that way. If you want to, it's your choice, but again, time consuming, right? Now, it turns out there's this savior sort of result in mathematics called the Chinese Remainder Theorem, all right? And it's stated like this. Now, this looks awful, it looks awful daunting, but it turns out to be remarkably easy to work with. Notice that we have three congruences here. So for our setup here, your n would be 3. We actually have 3 congruences here. This is a general statement for any number of congruences. Now, one of the conditions is they want, for this to work effectively, these moduli, 13, 15, and 19, can't have any common factors. That's what this means right here. It just means that these numbers here, the m sub i's, can't have any common factors. Now, what they do, this result depends on the product of all of these moduli. Like here are our moduli, I guess that's the word, moduli. Our moduli are 13, 15, and 19. And it turns out the product is very, very important, okay? And now, there's some things here that look a little, they're both, but it's really not that bad. This is a summation symbol, so we're going to have 3 sum-ins because we have actually, again, we have 3 congruential equations here. Now, so your a sub I is easy enough. That's just these numbers here. There's 8, there's 3, and there's 15, right? So 8 here, right? Is that going to highlight for me? Yeah. Okay, and then 3 there, and then 15 there, right? So these guys here are your a sub i's, all right? Now your b sub i's are just the numbers with one of the factors canceled out. And you can just go along and see this. Your b sub I is your capital M divided by whatever your moduli happens to be at that point. Okay, whatever your moduli happens to be at that point. So the 3705, which is the product of the 3 moduli, divided by 13. And let me come down here, folks. Okay, so there we go. This is actually equal to 285. All right, and you can do the arithmetic on that, but I've done it for you. Now, this is kind of the troublesome thing here. This -1 doesn't mean like you might think. It's not just the arithmetic inverse where these would cancel out and you would get 1 here. This is called the multiplicative identity modulo in modular arithmetic. Okay, now so let's come down here a little bit further. So if you'll notice, the 8 and the 285 survive, but what you get right here is 12 here. Now that takes some understanding, because how in the world that you see these 2 numbers right here, this is 285, that's 285, that stayed 285, and now we're trying to find the inverse of 285. But you see 285, if you reduce it modulo 13, returns a remainder of 12. Or what I'm saying is 285 divided by 13 would leave a remainder of 12. That's where this 12 is coming from. Okay, that's where the 12 is coming from. 285 divided by 13, what's that? Oh gosh, who knows what that is? That 21 times 13 is 273, right? And so you would have a 12 remainder there. So again, if you divide 285 by 13, you get 12 as a remainder. Now the hardest part of this is, how in the world did we come from here to here, right? From there to there, from 12 inverse to 12? How did that even happen? Okay, that looks absurd. Well, it turns out in modular arithmetic, something can be its own inverse. Now, let me come down and show you, this is a little tedious here, but 12 inverse is not the standard inverse that you've learned about in real numbers. It's the solution to this congruence right here. If you think about this like reciprocal notation, 3 times 1/3 is equal to 1. It's the very same thing. 12x is congruent to 1. That turns out 12 itself is the solution. That's crazy, isn't it? But 12 times 12 is 144. 144 minus 1 is 143. And that's a multiple of 13. 11 times 13 turns out to be 143. So 12 is its own inverse. I know that's crazy. So I know it looks like a typo going from here to here, but it's not, folks. Now, I didn't work out all the rest of these in detail, but you can kind of see it's the same sort of pattern. See if you can see where this number 13, which turns out to be the inverse, this number 4 over here comes from, all right? Verify that. I don't want to clutter this up or make this last too long and leave some of it to you. But it turns out when you do all this work, and then you have to take the remainder upon division by 35. That's what all this says, folks. Is you add up all of these numbers here. All these numbers, when you add them, all this stuff, when you add it up, ends up being 48,593. Now, what this means is divide this number this number right here by 3705. And when you do that, you'll get 528 graduates. All right, it's amazing. To me, this is just astonishing that with scant information, you could actually get the answer. Now let's come back, 528, last thing I want to talk to you about. Look what happens when you put 528 in here, right? That would be, how many rows would that be? Gosh, I don't know. But guys, you can verify all this. 528 satisfies. I'm trying to think what, okay, it does. Look, folks, if you have a 528 right here, 528 minus 8 is 520, and 40 times 13 is 520, right? So this first one would have been 40 rows. Would have been, R1 would have been 40 rows of people graduating, right? Tossing their mortarboards. Now, y'all, right here, this would be, if that was 528 there, 528 minus 3 is 525. And that is some multiple of 15. I don't know what it is off the top of my head. But what I'm trying to tell you is that 528 would have appeared in all three of these sets. 528 would have appeared in all of these sets. Let's see, can I still write here? 528 would have eventually made an appearance in all three of these sets had you had the gumption or the lunacy to take that approach. Y'all, I hope you like this. It's called the Chinese Remainder Theorem. It actually was invented by the Chinese, apparently. In warfare, they would line up their troops, allegedly. I don't know if that's true or not. Different ways, so they would know how many they had, but they, you know what I mean? They would line them up differently so that I guess the enemies couldn't count them as easily. I don't know. Something, but it, excuse me, apparently it did have a military sort of ruse, the deception sort of thing. But anyway, I've talked enough. Sure hope you enjoyed the video. Thank you.